All right, so congratulations. If you're watching this video, you've made it all the way through landing gears and brakes, wheels, and all that good stuff, which is a lot of information, especially whenever you take hydraulics and you nest it in there with it. There's a lot to process if it's your first time through. Now we're actually going to get into a more fun, in my opinion, a more fun subject matter, which is going to be aircraft auxiliary systems. Now, auxiliary systems is kind of a loose terms, like because the fuel system is in this class, but it's not really an auxiliary system. It's not kind of ancillary or a nice shiny thing to have. It's something you absolutely have to have. So we're gonna go through all these different systems, and an airframe has a lot of different systems, especially whenever you start talking about like heavy commercial aircraft. They'll have multiple layers of systems that all talk to each other, and one thing can go wrong in one and cause just a cascade of shenanigans all throughout the aircraft, and you have to like know how to troubleshoot them effectively and isolate some of those systems apart. And to begin to troubleshoot effectively, you really need to understand how they work, what they're for, and why they're there. So in this first video, we're going to start talking about ice and rain control. Now, rain control is basically boils down to wiper blades, but ice control, on the other hand, is a pretty significant and severe threat to aircraft that are flying in IMC. Your heavy weather, fog, rain, snow, that kind of thing. Now, there's a whole host of different types of ice control systems that are out there, from anything from de-icing boots to heated leading edges to even these porous skins that secrete fluid like TKS, which is super slick glycol type substance. Anyways, so just buckle up. We're going to start talking about like, what is wing icing? Why does it matter? Where can it be found? And then we're going to progress into the systems that are out there and how you maintain them. What are some of their common problems? And then we'll finish it up with like looking at what are the ice control systems on board a 737 MAX. Okay, so this is American Airlines flight 4184. It crashed just outside of Chicago in 1994. Due to icing. Now, you wouldn't think that in the kind of the modern era that an aircraft could crash because of something like that, but it happened. What happened is they were in a holding pattern outside of Chicago, and as they were holding, they were descended into 8,000 feet. As they went into there, they encountered freezing rain that they weren't. No one was really expecting. Now, they had the ice alarm went off. They had turned on the anti-ice system, which was heated boots on this ATR 42, I believe. And that ice that was on those boots fell off. However, they had also dropped the flaps to kind of slow down while they're in this holding pattern. Well, as the flaps came down, it caused the wing to pitch up slightly. All right, and as it pitched up, it created just enough surface area behind the boot for the ice to continue to build up. So this ice builds up, and whenever the airplane starts to sink because it's not producing enough lift, the airspeed starts to come up. As the airspeed comes up, it all of a sudden sends an overspeed alarm or turns an overspeed alarm off. So they then retract the flaps, and as they retract the flaps, it was giving them the last little bit of surface area that they needed to maintain, the lift they had accumulated. Well, as that happens, the plane entered into a roll, and as it rolled, they just basically were never able to over. Now, this just goes to show how serious ice can be to an airplane. It's not something to play around with, and it's one of the things you go get your private pilot's license. This is all going to be on the oral portion of that, where they ask you, hey, what are the different types of ice? How does ice form? all that good stuff. Pretty much anytime that you have temperatures that are close to freezing or below freezing, and you have moisture in the air, ice can form, and it will be a thing throughout your career as a maintainer to always be maintaining de-ice systems on props, on airframes, on engines, you name it. Ice is a reoccurring theme across maintenance period. And you'll even see ice damage where ice forms on props, gets slung off, and slams into the side of airplanes. Okay, so why is icing so bad on an aircraft? Now, here you'll probably remember this from general, like the four forces that act on an airplane in flight. Now, as that ice starts to form on those airfoils on the tops of the wings, it doesn't produce as much lift. Like laminar flow starts to get disrupted, and you have disrupted flow that doesn't allow for lift to actually occur. So as that lift decreases, it becomes harder and harder for the airplane to stay in the air. Now the thrust will stay, constant. Let's say you've got it firewalled, the engine can only produce so much. The weight's not going anywhere unless you start throwing people out, I guess. And the drag could potentially increase, and that just basically means that the airplane is eventually going to nose over and crash. Now there's other factors as well. If ice forms like it did on that airliner, on the flight controls, they could get jammed up, and then you'd end up having to like yank on the controls to see if you can potentially break that ice off, which is going to be very if it's that to that point, you're probably not going to be able to clear the ice, and you'll end up inducing some sort of adverse control that you don't want, and then into the ground you go. Okay, a couple examples of ice on aircraft. Leading edges of anything, be that the wing, the horizontal vertical stab, the engine cowlings, whatever, are always very, very susceptible to ice. And most of the time, on your more mature aircraft, you're going to have anti-ice systems that are built into it to basically prevent this exact thing from happening. So you can imagine the lift getting spoiled on this, in particular airplane as the air tries to travel over the top. But pay attention to leading edges for ice. So another one that'll happen is propellers. If you don't have an anti-ice system in the propellers, and most propellers that are out there these days, except for small GA planes, they're like VFR rated only, not really true cross country planes. Um, they'll end up having anti-ice systems built into their props. And what you'll see is that like as you're flying, all of a sudden like your RPM start to go down because the heavier and the more disrupted that flow is of that prop going through the air, the more the engine has to work, and the engine is already kind of maxed out at a certain fuel setting. You'll see the RPM start to dip down, dip down, dip down, dip down, and that's how it's one of the indications that you'll know that you have propeller icing. But this can be really dangerous because whenever that ice breaks off, it gets slung off, and this is how you'll end up seeing like massive dents on the sides of like DC-3s, your older prop planes that you can like look out the window and directly see a prop right there. You're going to end up seeing that ice come off and impact the fuselage directly on most models. All right, here's another one that's largely been mitigated by pitot heat. So like there's your pitot tubes, and you can see that they're completely iced over on a plane that landed. Like I said, notice this black and white's older because most people have come around and they've put pitot heat installed on their pitot tubes to prevent this exact thing from happening. They get ridiculously hot enough to where don't turn that pitot tube on if there's any kind of flywigger on it because it'll melt right through it. And so that's something that to kind of like as a kind of a maintenance stand towards the maintainer is be very very careful handling those things until you know for sure that that pitot heat's off because it'll burn you to no end. And so, but anyways, this is a place that ice could form if that were to happen. Your indications of the cockpit are pretty straightforward. The anything that involves ram air, which is basically going to be your airspeed indicator or airspeed indicators, like I said, anything that uses ram air will get plugged up, and it'll the plane. It doesn't matter what you do, the plane is always going the same speed, and it's kind of like, oh, that's curious. But yeah, like I said, rare to see this happen just because the pitot heat works. The only time that you would probably see this happening is that if the pitot heat were to fail, and then most, especially your heavy commercial guys, they're going to end up giving you an indication that, hey, look, the pitot heat's not working, and you'll know that without having to look out and see the pitot heat caked up in ice. Okay, another one that's pretty dangerous is icing on windshields. Now, this in particular scenario, this is a like a cabin window where it's iced over on some big transatlantic flight, and it's largely because you don't see a whole lot of icing pictures of cockpits because they have heated windshields. They'll blow heated air over the top of it to keep it from happening. There's films, all kinds of things we're going to get into here in just a little bit to prevent that exact scenario from happening. But like you can just imagine not being able to see as you're coming into land, even in like an IFR landing, you're still like you have to do a missed approach if you get down to a certain level and you still can't see the runway. Well, most of the time you can't see the runway because of fog or some sort of weather condition. It's a lot harder to be able to find the runway or if you can't see out the airplane. Period, regardless of what the weather is doing, and so there's a lot of effort that's gone into trying to prevent this exact scenario from happening inside the cockpit. Now it'll still happen on the passenger windows and stuff, and that's not that big of a deal. This means that Grandma can't see what she's flying over, but she'll get over it. But yeah, so these are all just a couple examples. You can also see ice get into the water and waste system lines and drains. So like they'll freeze up at certain altitudes if they're not properly routed, or they're whatever DI system is for that particular system isn't taken care of. And then antennas are another big one. So like antennas stick out there. If they start to collect ice, then the signal gets degraded and you can't be able to transmit. So that's where you'll start to see like intermittent faults become a big thing. That the pilots will say like, "Hey, look, we were trying to transmit, they couldn't read us, or we weren't getting a signal from X, Y, or Z system." And then you're like, okay, you go and you do a bit check on it on the ground or a bite check, and it passes. Then you sit there and you do a maintenance operational check. So you actually try to use the system, and it works just fine. And so then you'll sit there and say like, well, I could not duplicate. You sign it off and whatever. Well, the pilot comes back, gets in the same airplane, is super mad because like he's having the same problem again, and he already wrote it up 2 or 3 times, and you keep saying you cannot duplicate. Well, the problem is that like the actual issue is an anti-ice system that's malfunctioning in that part of the plane, and whenever he gets up to altitude, it ices over, and then it kills that system because it can't transmit. Because effectively, you've taken an antenna and turned it into an ice block, and so it's something to keep in mind as well. Okay, so now that we understand why icing is bad, how do we know that icing is actually occurring anywhere besides just simply seeing it? What are the ice detection systems that are available out there to the everyday pilot? Now, if you look around a heavy commercial airplane, generally you'll see these really wacky-looking probes that stick off to the side, and then there's several of them that are out there. This is one version. Effectively, this little strut hangs out, and you can see it's shaped as a mini airfoil. And as it goes to the air, if ice starts to build up on it, the probe there will start to detect it because all of a sudden it'll start to see that, hey, look, there's ice that's starting to accumulate. Now, this will give you a warning in the cockpit, and it'll also start turning on the anti-ice systems automatically to keep the plane safe. Now, in general aviation, you generally don't have things quite that sophisticated. Your ice detection system is more or less limited to your eyes and just simply monitoring the weather conditions that are outside of the plane. However, as time goes on, there are companies that are coming up with affordable options for ice detection, such as this Safe Light ice detector that's here. Now, it basically works the same way. It gives a surface for the ice to build up on, and then detects it using the probe on the back end. But for the most part, the only true blue ice detection systems you're going to see are going to be on heavy commercial aircraft. All right, now that we know that icing is occurring on the aircraft, what do you do about it? What are the systems out there that are available to aircraft owners, pilots, to get that ice off so that way they continue to fly safely? Okay, so there are 4 basic ways that you can prevent ice, all right? Or fight ice whenever it starts to form. There's heating air surfaces, or heating surfaces with hot air, heating by electrical elements, and then breaking up the ice formation usually by flexible or inflatable boots, and then a chemical application. Now, this table that you're looking at here gives you locations that are very common to have ice buildup on, and the general modality of fighting that ice. We're just going to start at the top and kind of talk through them, and then we're going to get into the details of every one of these systems as we go. All right, so first, leading edge of the wing, most commonplace. It basically happens to everybody at some point or another if you fly around. There's ways to do this. There's thermal pneumatic, thermal electric, chemical, and pneumatic de-icing boots. So like thermal pneumatic is going to be just like heated leading edges, like you'll see on the Learjet, or thermal. Excuse me, that's thermal electric. Thermal pneumatic is heating through bleed air systems. So basically, you take hot air from the engine, you pipe it through a series of tubes that heats the leading edge up and keeps the ice clear, because it's just like super duper hot on the leading edge there. Chemical would be like TKS or some sort of glycol. It basically secretes that chemical out and keeps the ice from adhering to the wing, and that basically creates a kind of a barrier and doesn't let it stay there. Now, the downside with there's a lot of downsides with chemical. That's why you don't see it on here a whole lot. But one of them is that you're limited to how much chemical you have on board. So just imagine like you're flying an airplane, especially if you're in kind of like the razor thin margins of usable weight. You don't want to sacrifice that for for glycol or TKS, because it's just really easy. Just don't fly in icing conditions. You don't have to worry about it. Anyways, and then pneumatic is simply the de-icing boots. So basically, boots will basically inflate and deflate, and what that's doing is it's physically breaking the ice off as it goes. Imagine like if you try to like freeze a balloon and then you went and squeeze the bottom of the balloon so that it inflates bigger. That ice just basically can't keep up with the expanding balloon underneath it, and it cracks and falls off, and then the balloon is deflated and goes back down, and that's how it goes. Anyway, so that's how you do leading edges of the wing. Also, leading edges of vertical and horizontal stabilizers, basically kind of the same surface, just arranged a little bit differently. Windshield, you'll get thermal pneumatic, thermal electric, and chemical. And then, like we kind of went over that, heater and engine air inlets. Basically, so like engine air inlets are airfoils of a type. We haven't gotten to the power plant yet, but essentially, like your big fan cowlings create shock waves to help manage the pressure of the air as it comes into the engine. Now, in order to do that, they do that by adjusting the camber of the fan cowl. Well, so whenever you start doing that, then you effectively have like another leading edge of a wing. So it's very similar in a lot of ways to the leading edge of the wing. One of the key differences here is that notice that you don't have pneumatic or chemical listed on there. Well, the reason being is that the pneumatics would change geometry of the fan cowl, and thus kind of defeat the point of the fan cowl. And then you would with chemical, you don't want to introduce that into a running engine, which would not be good for anything. So you're kind of limited to the ways that you can de-ice an engine. Pitot heat and static air data sensors are thermoelectric. That's pretty much universal. I've never seen any other way to do that. A propeller blade and leading edge and spinner, you will see chemical on those that they'll basically start at the hub, and then they'll squirt like de-icing fluid on there, and it'll stream down those propeller blades, and they're pretty effective. It does make quite a mess though, so that's kind of a downside on that one. Carburetors. This says chemical is out of the 8083. I've never actually seen a chemical carburetor, but hey, maybe it's out there. But thermal pneumatic, 100%. Even on small GA airplanes, what they're going to do is introduce hot air into that venturi and allow that ice to melt and go away. And the engine will just simply just like pass the water, and it'll be no big deal. And then lavatory drains and portable or potable water lines is thermal electric. So it's basically making sure that those drains and water lines are routed correctly and heated where they need to be heated at to keep it from freezing up. Not that it's the end of the world if you can't use those systems on board, but if they were to freeze and bust, and then whenever the plane lands, it starts to leak, that could be really, really bad. I mean, for instance, the 37 Lav is basically directly over the eBay, and you'd end up having a lot of that fluid leak down into the eBay. and cause all sorts of electrical problems. So those are kind of some common ways and places in which you can see de-icing methods. Okay, so here's the architecture for a thermal pneumatic system. Typically you'll see these on business jets, heavy commercial aviation. You'll The way that these work, generally the engine produces bleed air. That bleed air then gets piped to the front of the wings and pushed through to an overboard outlet on the side. Now, what that does is it helps circulate extremely hot air in those wings. Now, you can see here some over temp switches that are uh, you know are denoted on the diagram from 350 degree over temp switch on the very leading edge, so it could get up to 350 degrees to touch one of those things. So that's something to keep in mind when you're catching an airplane. It might taxi up to you, but you don't want to go out there and just start putting your hands on stuff, because if they have one of these systems on board or working, it could very well burn you. Notice that it gets cooler the further in it goes. So you lose from 350 down to 212. That's a 100-degree drop in probably about 2 feet. The reason being is that like you're getting closer to other systems. There's usually going to be like fuel cells that are inside of the wing, and so you don't want to get it as hot. You also don't have the same need for such high temperatures, except for on the very very leading edge. Okay, so here's the inside look of what a leading edge or heated leading edge potentially could look like. Notice you have the front spar in the back, and then you essentially the leading edge, whenever you go to install it, is more or less just a bent piece of sheet metal that just gets riveted right there on it. So inside you have this blank space. Well, inside the space, they'll place a leading edge diaphragm that will allow that air to circulate around right inside of that leading edge, and then bypass it to come and dump into either the exhaust, or if you follow it around the top, into that blank space behind the diaphragm. So that concentrates the hot air up front where it's needed the most, but still allows it to circulate and not overpressurize, and also heat the rest of the wing up to a certain degree. That allows for the ice that's forming on the edge of the wing to get melted and fall off, or ideally just never form in the first place. Okay, so on a heavy commercial aircraft, this is typically the kind of systems architecture that you'll see for a what is often called a WAI, like wing anti-ice systems. So in the heart of it all, you have ASIPs, which more or less basically looks for air or looks for ice, and then detects it, and then does something automatic against it, so long as that it's engaged, which it should be anytime the aircraft is moving. ASIP stands for the Airfoil Cowl ice protection system. So essentially, what ASIPS is going to do is it's going to take data from all of these other black boxes, or your LRUs, and it's going to analyze it and then make a decision to turn the bleed air on, bleed air off into by way of these valves and pressure sensors up and down the wing. Now, you can always turn the anti-ice system just on, but generally speaking, it's always set up to auto. Reason being is that you don't need to run the risk of having hot air being piped into the wings if you don't necessarily have to have it there. And if you know you're going to be flying into like icing conditions, like you're flying into O'Hare in the middle of February and there's a snowstorm, well, you can just go ahead and turn it on. But if there's always just a chance, always put it to auto. The reason being is that you don't want to sacrifice the safety of that system not being on for a condition that like may or may not exist. But just kind of keep that in mind. And one of the things that I keep hammering on and I want you to take away is that look at how many different systems talk to ASIPs, and how many systems ASIPs talks to all the other systems, and the consequences if something goes wrong. You could have either a failure whenever you need it, or you could have a failure that it's always on whenever you don't need it, that could result in a bunch of heated slats that you don't necessarily need. Like if let's say like the ASIPS decides, hey, look, we're going to turn the wing anti-ice system on, and it's going to land in the middle of July, and some guy walks up there not thinking that it's off and touches it, you could potentially hurt somebody. There's also an interesting stat that like the majority of all aircraft fires are caused by anti-ice systems, and the reason being is because you're piping super hot air into these confined spaces, and so if there's anything up there that can catch on fire, it's probably going to, because you're going to be above the flash point of a lot of different substances that we work with on a regular basis. So if there's any sort of a FOD problem, or just degradation for being used over a long period of time, or damage, you could end up having a serious issue if you just start dumping bleed air into some sort of space that it's not supposed to be. So just know that ASIPs is going to come back whenever we get to the 3.7 Gen Fam on anti-ice. Okay, so this is what the actual piping looks like, or the ducting for the wing anti-ice system in the slats specifically. Notice as the slats come out, there is a inner and outer telescoping duct that allows that ducting to stay together, and then pipe that hot bleed air down to the anti-icing spray ducts on the leading edge, and then that air more or less just swirls and then exits the aircraft from there. Just kind of an idea. You'll see these if you're ever having to work slats for any reason, or troubleshoot. In my case, troubleshoot electrical issues in the slats and the wiring and stuff like that. You'll end up seeing these ducts there. If you happen to be working on an aircraft right after it's run, these things are going to be super duper hot. But hopefully you can avoid that. But just to kind of get an idea in your mind like what those systems look like and what to be looking for. Okay, here's the logic diagram for a wing anti-air or wing anti-ice system. Notice here the things that can inhibit it. The airplane being on the ground, so once the aircraft goes into ground mode, it's going to turn all this stuff off and let the wings start cooling down, and that's for just general safety of your ground handling guys, and also to keep the airplane from overheating those wings and starting to fire. Just keep in mind that the way that system is built, it's taken into account the air going over the top of the wing, and it's also cool air because ice is forming into it. Well, if it's just sitting on the ground and those systems are on, it's just going to get hotter and hotter and hotter, and it can get to a point where it's over temperature and causes all kinds of problems. A total air temperature of more than 50 degrees Fahrenheit, and the time since takeoff is less than 5 minutes. So, like, essentially, it's going to be inhibited if the air is above freezing by a certain margin, because then you won't have ice. So the ASIPS guys are going to say like, "Hey, nope, we're going to turn you off. No big deal." Auto slat operation. So if the slats are in auto, it'll inhibit the wing anti-ice system from kicking on. Air-driven hydraulic pump operation will also turn it off. It's also turned off during engine start. It's a high demand time for the engine, so it basically shuts off all these little ancillary systems, so that way the engine can use all of its power to basically get started and running, and not have to feed all these other systems until it gets up to a certain ENG. Bleed air temperature less than 200 degrees. That basically means that the engine's not producing enough heat anyways, and so it's going to shut the bleed air valve and keep all that heat inside the engine, rather than trying to pipe it out where it's going to not do any good anyways. But those are different systems. There's different ways that you can see the wing anti-ice system basically just turn off. Now, the reason we bring that up, and the reason we look at that, is because we want to make sure that we understand all the different possibilities that could cause a anti-ice failure. That helps us with troubleshooting. It helps us with also understanding the gravity of what we're working on. If we're working on, say, like an ADARU or an AIMS or an FMCS or whatever, that, like, if you stray too far from what you're working on, you get careless, you can inadvertently cause more problems than you're fixing. So you want to always stick to the manual and do exactly what you're supposed to be doing, and do it with a high degree of professionalism and fidelity. Because if you do something weird, or like bend a pin whenever you're putting a box in or whatever else, you could inadvertently cause one of these inhibitions to kick on, and that could be whenever the airplane needs it the most. Like you've got, if the airplane believes that it's on the ground, well then all these systems won't come on, and so they're going to take off and be like, hey, why isn't X, Y, or Z thing happening? Well, it's because like you accidentally put the airplane in ground mode, and it still thinks it's on the ground. You could, if you were to say damage a wire to a temperature pickup somewhere, then it's going to believe, hey, look, the bleed air temperature is below 200 degrees, so we're going to turn the anti-ice system off. Any number of those things. So you always want to understand that, like, whenever you're working on something, you're not working on just the one system. You're also working on all the other systems that are connected to that system. Okay, so wing anti-ice system is a bleed air system, a thermal pneumatic system. This is thermal electric for the pitot tube. So here's kind of the wiring diagram for the left pitot tube probe on a kind of a notional airliner of some variety. And what I want you to kind of take away from this is more of kind of the system integration piece and the things that could potentially inhibit it. Now, if you can start to memorize or at least get a good feel of the things that will inhibit certain systems from working, you will become a much better troubleshooter. Like, because if once the pilot writes up, it's like, hey, like the left pitot probe basically failed to activate its heating element for whatever reason. Now it could be the pitot probe is bad, or there's bad heating element or whatever else, but it also could be any number of these other systems as well. So like for instance, if you look at the air data module, it says like in the air or greater than 50 knots. Okay, so if something is starting to fail in the air data module, there's a leak in the line somewhere. It can all throw those things off. So a lot of times these systems are not like the symptom is not necessarily the problem. It's just that's where it's manifesting it, and you're seeing like, oh look, the pitot heat didn't come on the left probe. Like it's not necessarily the pitot tube that's actually the problem. It could be any of those other things. And if you look at Ames is fed by the Adaroo, right? The Adaroo basically touches everything on there. AFDC, PFC, all these buses share data and then take data from each other, and you could have a problem anywhere in there, and it's just starting to manifest here. The airplane could be stuck in ground mode for whatever reason, even though that would be unlikely. Or you could have a power problem. Let's say that like there's a ground heat control relay there on the left hand side of the P10 power management panel. That relays are notorious for going bad, and so that relay could be out. If that relay is out, then it's never going to get the power to it. So you might need to start there and just see, like, hey, look, pull a connector off and just turn the pitot heat up and see if you're getting power to it. If you're not getting power to it, then you know you need to go further upstream and start to work your way into it, rather than immediately just assume that the pitot probe is bad and then just change it out. That's what we call shotgunning parts, and you just start throwing parts at it without actually understanding the problem that's there. But the how the de-icing system works side of it, effectively, it's just a big electrical heating probe. It's going to pipe a certain electrical value into the pitot tube. It's going to ground it out. Then the pitot tube becomes basically a big resistor, or has a resistor in it, and then that generates electrical heat. It does it very effectively and gets very hot and keeps it going. But you're going to see this same kind of system, the same sort of architecture, pretty much in any of the different systems that are thermoelectrically heated to prevent ice from showing up there. Okay, and here's some examples of places that you can get thermoelectric anti-ice systems. You have anything from the angle of attack sensor on both sides, the pitot tubes, the ice detector itself. Could potentially have it. The center pitot probe, so there's always going to be like two on either side. You have left, right, and center. You're going to have it on any pitot tube that's out there. You also have the P2T2 probe, which hangs down inside the engine cowling, which we'll get to more of that when we get into power plant. But effectively, it does the same thing as like your TAP probe. It looks very similar, and it helps the engine basically optimize its air fuel mixture based on the air that's coming into the engine itself. But they're susceptible to icing, just like the leading edge of that cowl fan is susceptible to icing, and so it has to have some methodology to keep that ice from forming. Let's talk about chemical de-icing systems here. This is a Diamond aircraft that has the TKS weeping wing that's installed into it. Now, the weeping wing is just a titanium strip that has over 800 holes drilled into it that are 2,500 thousandths of an inch in diameter, like very, 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 very small. And whenever you start to see it actually weep the TKS fluid, it looks like it's just all of a sudden producing water because the holes are so small you can barely see them. But effectively, what this does is it comes out, the fluid more or less is very, very sticky to the wing, but it provides a layer of fluid to prevent ice from forming on there. Now, this is extremely effective at melting ice, and it's extremely effective at preventing ice from going onto it. The challenge becomes is trying to keep the TKS fluid on the wing for the length of time that you're actually flying through, like IMC conditions, which you generally speaking don't have enough TKS fluid to get to where you're going. So this is kind of like a last resort sort of system. Okay, here's a notional TKS distribution system on a small GA airplane. Notice it starts with a tank, goes to a metering pump, and then gets distributed throughout the aircraft using like on here they have 5/16 nylon tubing, which is basically just kind of like feels like a plastic tubing, and then it goes to these distribution manifolds. Once it hits those, they get proportioned out equally or based on the area that they're expected to cover. And you have orifices that secrete the fluid on the wing now, or on the vertical stabilizer or horizontal stabilizer in the back. The other one that I really want to kind of orient your attention is the spray bar for the window. So basically, it will spray that TKS fluid up on the window to help clean it off. And then there's a slinger ring on the prop, which basically, as the prop spins, it emits a little bit of TKS fluid right above the blades themselves, and it gets strewn out all up and down the propeller blades and off the ice goes. But that's like I said, I keep using TKS. There are other systems that are out there, but by far it's probably the most common that you're going to encounter. Now I'll tell you just as kind of like one mechanic to another. Don't let this stuff just sit on the hangar floor because it is clear and you won't see it, and it is the slickest substance known to man. So you'll be walking and like you'll hit an old TKS spot where somebody didn't clean it up right, and you will absolutely bust it. I know this because I've done it multiple times. When I worked in GA in Seattle, TKS was pretty common to come across because it's low complexity, low cost compared to some of the de-icing boots and things on smaller airplanes, and these guys would use it. Well, whenever we would go to service it, almost always some would drop off on the hangar floor, and you would wipe it up and wipe it up and wipe it up and wipe it up, and it never seemed to ever come up. Well, what would end up happening is like 4 or 5 weeks would go by, and you'd be pushing an airplane, and you'd hit that same spot on the hangar floor, and out your feet would go, and boom, like on the ground you go. So just try to be as diligent with this stuff as you can to not spill it anywhere, because once it's on the ground, it becomes very, very difficult to clean up, and it becomes very, very dangerous if you step on it. Okay, so probably one of the most effective and safe de-icing methods is de-ice boots. Now, you won't see these on heavy commercial airplanes, and generally speaking, you won't see it on small GA airplanes, even though you can get some STCs for some of them. So you'll see the occasional 206, 182 run around with de-icing boots on there. But by and large, they're most common on business aviation. That kind of like middle class airplane, so like King Air 360s, some jets, and then a lot of this is a Seneca, if I'm correct there, and like you'll have like Seminoles and that type of thing. That's where you're going to find your de-icing boots to be used. Now, effectively what they do is they're going to inflate and then they're going to deflate to cause the aircraft to or the cause the ice to break off of the airplane. Now, there's a couple of different styles of boots that you'll see out there. This is one that I'm most familiar with. You'll see them on like King Airs, where you'll have different valves will open and close to inflate different parts of the boots. And so, like effectively on that bottom picture, you'll see one row inflate, and then the other one deflate, and then they'll reverse it. And what that will do is we'll keep the ice from sticking to the leading edge of that wing because it's basically pushing it off like every couple of seconds. Now, whenever it's not in use, the air pump that's being driven by the engine still uses or still works, still runs, except for it's set up so that way it sucks air out of those boots. That causes the boots to suck up close to the wing, and you don't have to necessarily pay in terms of airspeed and performance for having the boot on there. It allows it to work just like it was just a piece of sheet metal and a natural part of the wing. Okay, so this is a sample de-ice boot system off of a twin-engine GA airplane. Notice that there's gyros tied into this, making the most out of having those two pumps tied to the engine. And it's really kind of straightforward. There's not a whole lot to it. Basically, the same things that you'd have in any other sort of vacuum system, just with a series of deflate and check valves to make sure that the air is going the correct way. It comes out on this particular system. They have a three-way T going to the left, right, and the empennage boots. Usually, you're going to have like a manifold or something right there. It probably just didn't include it for the sake of simplicity of the drawing. One thing to point out is that it still uses an inlet air filter. So anytime that you're going to do an annual, you're going to have to replace that inlet air filter, and that's something that a lot of people don't appreciate or don't know or understand unless you've done a lot of GA maintenance. But usually those are located up behind the instrument panel. You're just going to reach up there, unscrew it, put it back on. They're usually never bad, but you do it every annual just to be thorough. Okay, so this is what it would look laid out actually on the aircraft. The thing to kind of take away, notice that you have pumps on both engines that they're going to come together at a control assembly and then get distroed out to wherever that air pressure or suction, I guess, really needs to go. Primarily in the two boots on either wing, and then the boots on the vertical stabilizer. And that's kind of a pretty typical arrangement that you'll see on these little aircraft. Now, de-icing boots have one thing that's going to get them is that they are temperamental. I mean, after all, effectively what you have attached to the front of the wing is a big, rubber balloon that's inflating and deflating, and that just naturally kind of lends itself to cracking and being susceptible to damage all the time. And there's also a lot of complexity to it, whereas you have filtering that has to happen. You have pumps, check valves, a bunch of different things can go wrong with it, and so you have to kind of stay on top of the maintenance, or else they could fail. And whenever they fail, it's usually whenever you need them. A couple of things to just remember with whenever you're doing any kind of boot maintenance is you don't want to put anything on them that could potentially damage them in any way. You don't want to lay tools on them. You don't want to run hoses over the cross of them or anything like that. They are very, very sensitive to anything metal coming across them, and you don't want to have to replace or repair a de-icing boot. Here's a list of things out of the 8083, just kind of like a troubleshooting diagram of what happens if it's slow inflation or won't cycle, whatever the thing may be. These are all just probable causes. But the actual troubleshooting will have to be done looking at that individual system, because they're not all uniform. They generally work the same way, but not all the time. And so this is a good place to kind of start and get your head going on them, but it's not necessarily the end all be all. Okay, so de-icing also occurs on the ground, and you've probably actually seen this if you've flown at all and been at the terminal. But one of the things that they have to do is actually prep the aircraft to taxi in adverse weather. And so what they'll do is they'll come out. They have de-icing trucks, and you have guys that basically just spray the wings off with hot water that has a fluid that's just mixed in with the water, and that blows all the ice off, so that way the aircraft can get started without any snow or ice on it. And from there, the aircraft's internal de-icing systems take over. But that's something that you may have to do, or maybe required to do, and just know that in order to release an aircraft for flight, that's part of it, is making sure that the aircraft is de-iced and ready to go. Okay, lastly, let's talk about rain. What exists out there to keep the rain from obscuring our vision as we come into land? Okay, so rain control is going to work a lot of the same way with the one deviation. So like you have hot air that can be blasted over the top of the wings. You can have chemical release that keeps the rain from getting all over the windshield and keeping it clear. The one that's fundamentally different is that is the wiper system, but it's not really all that complicated. It's pretty much exactly like the windshield wipers in your car. You can turn them on, turn them off. They have wiper blades, and they just simply squeegee the window for you as you fly along. Now, some aircraft have them, some of them don't. Some of them have a combination of different rain control techniques, but that is what they look like. Okay, so if you are on a aircraft that has a flight deck rain repellent canister, this is what they look like. Essentially, you're going to have a pressurized can that has fluid in it, and then whenever you select it, it will release that rain repellent through a little nozzle with the up in front of the window, and effectively it's just like Rain X on your car. It sprays on there, helps displace the water, so that way you can see through it. Now, however, the thing to keep in mind is that there's not a lot of fluid in there, so it's not going to last just too long. And so it's one of those things that you only really want to use it whenever you absolutely are ready to land, or you're looking for traffic, or whatever the other thing, whatever the thing is. So just kind of like TKS, only use it whenever it's time to use it, and for as short of time as you can get by with. Now, another one of these systems that helps with obscured vision is defog blowers. Now, effectively, all these are just there's a fan that comes up to a duct and it blows it over the windshield, just exactly like you have set up in your car. As you expel air out of your mouth, there's moisture in it. It hits the cold window and then starts to fog up. And so the best thing to do is to simply keep some warm air from going over that's dry to help dry off the windshield, and that keeps the fog from taking place on the air windshield. Now, I will tell you, of all these different rain control systems, most of the time you rarely mess with them. The defog blowers, though, they absolutely get messed with on a regular basis. It seems to be like they always want to go out for one reason or another. Even on the OH-58, which has it's basically, we flew without doors all and stuff. We were always seem to be replacing these defog blower motors on a regular basis, and they were an absolute pain. And they're always a pain, no matter which aircraft you seem to work on. So just kind of mentally prepare yourself to be changing out defog motors if you go and work the line, or you end up working avionics or anything electrical like that. That seems to be just one of those things that occur on a regular basis. Okay, so another way, and becoming more and more common, is the heated windows. So just like on the windows of your car, if you want to defog them, you can or defrost them, you can turn on the defroster, and you can see the little lines that are like these very, very, very thin wires that go across the window, heats up the window, and helps melt the glass, or melt the ice on the glass. These are basically the same thing, except for an aircraft window has to be able to withstand a 4-pound bird striking it, and so the construction is a little bit different. But effectively, you have these different plexiglass plies with either wires that are very, very, very thin, or a conductive material of some variety that's usually clear. They put it all together and then they pressurize it so that we basically you take like a kind of a sandwich structure and you squeeze it together super hard, and it makes it like into one piece. And then it gets installed on the aircraft. You hook up the window to the airplane, and then whenever you decide to turn on the windshield, it will start to get hot as it conducts that electricity and it converts it to heat, and it'll melt anything that's on there, to include rain, fog, ice, or whatever. So far more effective, a lot less moving parts than just about any other methodology that you'll see out there. So expect to see this somewhere out in the wide world in the future. Okay, kind of the last little ancillary heating system that you'll see on there is on heavy commercial aircraft, the ultra midsize business jets, and even some smaller jets. You'll have water systems, and that's sometimes it's potable water systems for the galley. Sometimes it's just the water systems for the lav. But either way, you're going to have to keep that water liquid, because what you don't want it to do is to freeze up and start busting things. So there's going to be some water heaters on board those aircraft, and you might end up seeing something pop. Now, depending on the aircraft and the arrangement, this could be a big deal if something goes wrong with them, and this could be kind of just like a, hey, look, we'll just like in-op that until we get to our next heavy check, and then we'll worry about fixing it. It just kind of depends on the operation. Just know that these systems exist, and then there's, even though they're just kind of nice to have for the passengers, they're still important, because what you don't want to do is have a busted water line somewhere on the aircraft, because that's not going to work out well for anyone involved. Okay, so let's bring all this together and look at the 737 MAX anti-ice system. So here's kind of an overview of all the different anti-ice systems that exist on that aircraft. We're just going to take it from nose to tail and just kind of talk through all of them. So first off, you have flight compartment windows. It has window heat, wipers, and rain repellent. So it has all three to help clean up the windows. The P5 panel there is just the control panel for a lot of this stuff. Then you have like the alpha vane each side, the TAT probe on each side, and the pitot tube are all electrically heated. So yet another kind of anti-ice system that's there. Then you have the engine anti-ice valve. We'll look at that here in a second. You have wing anti-ice systems that run the leading edge of the wings. You have your water service panel, drain mast heater, and waste tank service panel. All of that is part of it. It basically makes sure that the aircraft doesn't have any iced up water on board. That drain mast heater, especially, I'll tell you, gets extremely hot. I've seen guys get burned messing around with them. And then you have the elevator pitot probe in the back. That will also have an anti-ice system attached to it that's thermoelectric. Okay, here's the wing anti-ice system, both with the slats extended and retracted. Hot air from the wing anti-ice valve flows through the leading edge supply duct to 3 telescopic feeder ducts. These ducts move the hot air to spray tubes inside the slat cavities, and the spray tubes are perforated and supply the hot air to the slat cavities. And the hot air flows overboard through the holes into the lower surface slat. All right, so this is the engine anti-ice system. It basically consists of the engine bleed manifold, which will be ducted up to a valve that's then controlled by a series of pressure switches, and then discharged out through the swirl nozzle in the front. Now, basically, what that's going to do is it's going to dump a lot of hot air in the front of the cowling, and as that engine air swirls around, it'll raise the temperature of that air and cause the ice that's around the front of the fan cowl to melt. Pretty simple system. It's just blowing hot air effectively. The only time that you'll end up really messing with that is that if one of those pressure switches goes out, and then you'll get a warning in the cockpit and you have to go fix it. Okay, so this is a 737's window heat unit. Notice that it's controlled by the dual window heat control units, or the DWHCU, which is down there in the eBay. Effectively, you have heat over the left and right side, and you'll get indications that they're on. And hopefully, if you turn it on at the right time and it works correctly, the other indication is that there won't be any obstructed vision in the cockpit. The things to kind of to keep in mind is that like they are primarily responsible for very particular windows, and then they have a dual functionality of being able to respond to other or to be able to control other windows whenever needed. And so, like, if you end up having a window go out, that'll be really important to verify. What you would do to troubleshoot that is just basically disconnect the CAN plug and see if you're getting power based on, and then start switching the different window heat units on or off, pulling circuit breakers to help isolate which DWHCU is faulty, or what wire run the problem exists in. Pretty simple to troubleshoot. Okay, so these are things to watch out for on the bottom of the airplane. Primarily, they're heaters that basically keep the water that's on board flowing and not a big block of ice. However, they all get very very hot. So like the aft drain mast and the forward drain mast, both places that you want to kind of pay attention to. It's controlled by the water service panel on the right hand side. And then there's a waste tank service panel as well that you'll get intimately familiar with as a new mechanic as you drain the lav. But just keep in mind that these drain masts do get hot. They're intentionally built to get hot and keep the water flowing, and so they will burn you, especially if they've been on long flights, been on for a long period of time.